You may have noticed that I skipped over the material in Chapter 8, which deals with rendering in the pipeline, primarily what goes on in the rasterizer, how we go from dealing with vertices to dealing with fragments, the two things that you control in your shaders. And one of the reasons, I mean, there's only so much we can do in one semester, and I've decided that I really wanted to emphasize things we can do with WebGL over the next few weeks, the few weeks we have remaining in the semester. On the other hand, I think there's sort of this hole in that we really don't know how are these lines and polygons being generated on the display, and I thought I really ought to say something about it. So what I'm going to try and do is stick in a little bit over the next couple of weeks where we have gaps between the material. So what I'm going to do in this lecture is give you sort of an overview of what happens when you go from vertices to going to fragments and where various operations happen, and then we can talk about algorithms if time permitting over the next couple of weeks. But one thing to keep in mind is that although we can talk about various algorithms for doing the various jobs, and those jobs are basically how do you generate fragments in the rasterizer, how do you do clipping, and somewhat some options for how you might do hidden surface removal. Those algorithms are really hard coded in. They're built into the microcode of the GPU, so you don't really have much control over them. And in fact, depending on what GPU you use, whether you're using a cell phone or you're using a graphics card, those algorithms could be very, very different. But still, we should say something about the potential ways we can do it. And also, this will get us into things we'll consider at the very end about alternate schemes to using a pipeline architecture principally. What can we do with a ray tracer? And there's a few other ideas I'd like to stick in before the end of the course. So we're going to try and do that a little, at least an introduction in this short lecture. So what we have is we have in this geometric pipeline, and we'll look at the tasks in a little more detail in a minute. We have to, once we get out of that vertex shader, which is operating on a vertex by vertex basis, you have to assemble those vertices into the primitives that the system understands. And principally, we're going to worry about assembling them into really the only choices are triangles, line segments, and points. We'll try and focus on triangles here. So you have to assemble the vertices that are coming out into these primitives so that you can do clipping and throw out things that are outside of that view frustum in perspective viewing, or once we've converted to clip coordinates and done normalization, as we discussed a few weeks ago, really we're doing an orthogonal projection in the end. So we have to, in a way, decide which pixels can be affected by each of these primitives that we've assembled so that we can generate those fragments. That's the process that's called rasterization. Historically, it was called scan conversion because you had a display that was a CRT, and it was generated from the top to the bottom, and each of those lines going across was called a scan line. And so you were converting from some high-level representation of the object to scans line by line, and so that we had the name scan conversion that still is associated with it. So what are the tasks? Well, we can say, I want to look at them again here and see where they're going on. So clipping does occur somewhere at the end of the geometric processing. So here's your vertex shader, and the vertex shader is converting to clip coordinates, and pretty much the clipping is going on over here in a pipeline architecture. You really want to throw away things that you can't possibly see. You may have objects that are obscured by other objects which you won't find out about later, but at least on a object by object basis we can decide which things are outside of the clipping volume and throw them away. So primitive assembly and clipping are happening over here at the end of geometric processing. The rasterizer is generating the fragments. So when we talk about algorithms for doing scan conversion, we're really talking about the rasterizer. And at present, the rasterizer is the one thing in the pipeline that you don't have control of. Although in the future, maybe we'll talk about a rasterization shader, and we'll be able to put our own algorithms in. But for now, rasterization is the one part that's really hard coded into that. Your transformations, well, they could be taking place in the geometric processing or potentially within the fragment processing. Now, some things like hidden surface removal that you might say, well, gee, why don't I remove things that I can't see up here so I don't have to deal with them in the rasterizer and I could maybe process faster. The difficulty with that is that it really makes a lot of things you want to do in the fragment processor a lot more difficult. So we play this trick where we leave things in 3D even though potentially they could be in 2D over here, and as part of the normalization process, and we pass that along so that we can do hidden surface removal actually after we do our fragment processing. So hidden surface removal is somewhere in here, in between the fragment shader and the frame buffer. Likewise for anti-aliasing, we can potentially do some whole scene things here that we talked about a couple of lectures ago. But the kind of anti-aliasing that's done in the hardware is generally done here, where you're just trying to put things in the frame buffer. Well, here, this is a pipeline kind of view. I want to sort of step back from that for a minute and look at sort of two general strategies that we can approach. And I'll call them meta-algorithms because they're not detailed algorithms, but they're sort of two basic classes we can put on top of things. And that'll, I think, help us understand what we could possibly do and the different approaches. So if we start with this idea that if you're going to render some geometry, that you've got to process every object that you put in. High level, low level triangles, every object has to be processed in order to generate the display. But likewise, if we look at the back end, we have to assign a color. I shouldn't say every object, to every fragment. We have to assign a color to every fragment so that every pixel on the screen actually has a color. So we have, essentially, you can think of then rasterization or the general process of rendering as there being two loops, something that loops over all the objects and something that loops over all of the pixels. And which order we do those loops, which is the inner loop and which is the object loop, totally changes the strategy. So one of those approaches is called the image-oriented approach because it works on a pixel-by-pixel basis. That's the outer loop. Or the object-oriented approach, where it works object by object, which is the object-oriented approach. So let's just sort of look for briefly at each one. I think it'll help you understand the difference between a pipeline architecture and its limitations and a more global renderer like a ray tracer. Okay, so if we take this objectist approach, says the outer loop is over every object, and over every object I have to determine which pixels that object will affect. Sort of hidden in here is the idea. We start off with the coloring every pixel with some background color or black or something. So this is where the pipeline approach works, is that we process each object independently and we keep track of the depths as we've seen, so we can do hidden surface removal at the end. Now the main limitation of that is that we've seen, and we've argued this multiple times, is that you can't do any kind of real global operations other than hidden surface removal, which you use this trick of keeping track of the depths in a depth buffer, this partial information that you keep updating. But in general, you can't handle any kind of complex interactions between objects, like light bouncing from one to another. You can do a lot of tricks that we saw when we talked about how you might generate shadows, but basically you can't do most global kinds of calculations. But the advantage is that it's very, very fast, that you process objects independently. If you have parallelism in your system at the vertex level or higher level, you get to process process a lot of objects in parallel because they're all being handled independently. So what do you really need to have available? Basically, the one thing you need to have available is the whole frame buffer, because when you start doing your rendering, you don't know which part of the frame buffer that object will fall into. It may be clipped out completely. So you need the entire frame buffer available. Now that's not an issue at all because you have so much memory available in your attached to your GPU that that having that amount of memory available for every object to have access to is really nothing. So the main limitation here is the lack of the ability to do global kinds of calculations. Now if you look at the image space approach, it says, okay, the outer loop is over pixels. So for every pixel, I have to determine which object projects on that pixel and which one is closest to the viewer if they're opaque objects. So the obvious one that fills that is a ray tracer, where you trace a ray that goes through every pixel, and now you see how that ray intersects with all the objects, and you pick, if they're opaque, you pick the intersection that's closest to the viewer. Now, the problem with that is obviously you need all the objects available. You don't need the whole frame buffer available because you're doing it pixel by pixel. But having all the objects available is a problem. And also you have this issue that if you're not careful, the complexity of this goes up very, very quickly. I should have probably mentioned this when I talked about the pipeline approach. The pipeline approach, the complexity kind of goes up linearly because as you add more objects, because you're treating each object independently, so sort of the complexity is really just it just goes up linearly at worst with the number of objects that you have, and it goes up kind of linearly with the number of pixels that you have to work with. It goes up, if you have an n by m frame buffer, sort of in k objects, then the kind of complexity looks like k and m at worst, and so it's sort of limited, and in fact you can show experimentally and sort of argue why that the running times actually for these kind of algorithms tend to stay constant. That the linear is actually an upper limit on them. Now the problem for image space approaches is that not only do you need all the objects available, but in some sense you're saying, well, what does this object have to do with this other object? And so you have a worst case complexity that's kind of like sorting, is that if you compare an object to all the others and then you know what the intersection of that object is with the others when it's projected, you're done dealing with that one. Then you compare the one of the remaining objects to all the others, and that's an O of k squared kind of calculation, and a lot of it is to try and get that down. So these image space algorithms can potentially have more complexity than an object space algorithm. But we'll see more of that when we talk, assuming we have time, about some algorithms. Now, the one sort of approach that falls sort of in the middle are patch renderers, and the reason I mention them is that as handheld devices and smartphones become more prevalent and the computing power of those keeps increasing, the kind of renderers that we see on them are somewhat different from the kind of renderers we have in either the image space or the object space approach, primarily because you have to do things with low power, and really that's your prime consideration. They tend to use what are called patch renderers, where you divide the frame buffer up into small areas, called patches, and then you figure out for each patch what happens. So you determine which objects up front affect each patch, and then you render that patch and then go on to the next patch, and those are very popular approaches within the smartphone industry. Okay, so
that's sort of the general ideas behind this. And as I said, if we have time, I'll explore some algorithms in depth. But hopefully, at this point, you've obtained books, and you can always look up some of those key algorithms. Now, one thing I do want to mention as finishing this is that this sort of ties us back to when we were talking about what we can do within the frame buffer and fragment processing and render to texture. It's really easy and informative, and again, it's kind of projects you might want to tackle, is to actually investigate some algorithms by creating a virtual frame buffer, which is a texture that you can write into. And then you can address individual pixels and start writing your own fill algorithms, your own line rasterization algorithms, and various other kinds of things. And it's kind of a fun exercise to do. You basically are creating really just one function that writes an individual pixel, and then your algorithm goes through its calculations and decides which pixels it wants to write, and you could see the result in a frame buffer of any size. So if you want to experiment with anti-alias algorithms, you could do that. Okay, so let's end this lecture here, and hopefully we'll have time to talk about at least a few of the key algorithms in future lectures.